Hi, I'm Angus, and in my eagerness to introduce you to the experiment, I forgot to introduce myself. So, without further ado, here's the experiment.
Hi EGB113 and welcome to ET1 or Electrical to Thermal Energy, also affectionately known as the fridge. In this experiment, the aim is to model how a fridge works in terms of factors that affect its temperature, for both in terms of the cold and hot sides of a refrigerator, and also to look at factors that affect its efficiency. To do that, we're going to use a device called a peltier, which is basically two pieces of metal with a semiconductor sandwiched between them. It's a method of transferring heat from one side to the other, to give a really basic explanation. To do that, you'll use this setup, the peltier device. You've got a power supply, you have a Pasco interface, which basically provides some of the sensor information back to the laptop, which is running the software that actually collects the data you need. The peltier itself, or the device itself, is this board. This here is insulated foam. It's basically to keep one side insulated. It's going to remain on for pretty much the duration of the experiment. These two pieces of metal with the semiconductor between, that's your actual peltier device. This part here is the heatsink, and these two little white probes are your temperature sensors used to measure the temperature before and after the heatsink. Just beneath it, you can kind of see it, is a fan, and to give it a better view, this is the fan on the underside. It's basically going to be pushing air this way, coming out of the device. You power that with a little on-off switch here, and this knife switch, you'll set it to heat pump and you go to run the experiment itself. Now, built into this device, there are also a couple of other temperature sensors designed to measure the hot and cold sides, and all of this is going to be reported on the software as well. A couple of other values you need later on will be the voltages and currents of your generator. Now, you don't want that from the generator itself, because this is what the generator says it's supplying. This doesn't account for any losses in your circuit or your device itself. So what you actually want is coming in here, you've got your inputs, which are plugged in on this one, and also all the sensors are up here as well as on this side. These will actually give you the accurate readings of your voltage and current coming in and out of this device. The hardest part of part A for ET1 is sitting and waiting, and there's a fair bit of that, but it also gives you a chance to actually answer the questions and figure out what's actually going on with it. Okay, to run the actual experiment itself, as mentioned, all of this will be set up prior to you coming in. You don't need to adjust the power supply, so please don't. You don't need to plug in anything or unplug anything. When it comes time to do part B, which one of my colleagues will run you through, your demonstrator will normally be the one who comes by and unplugs everything and sets it aside and then sets up the next part. So please don't plug or unplug anything. We'll have a screen recording so you can better see this. It's a bit difficult to see on the camera. But the way this basically runs is this is at about 6 volts, under an amp. Any higher than that, we risk damaging this. I've already got the fan running. You can probably hear it whining away in the background. And that's just from that little fan switch down there. On here, on the software, we will have down here a little button that says record. You want to click that before you flip the knife switch. Once you hit record, a couple of things light up, your voltage. On this one, it's recording a bit funny, but normally you get a better result. You shouldn't actually get voltage out into the negatives. Part of this is also going to be because the knife switch isn't actually flipped. That's an important thing to remember. Down here and along the side, you've got a graphical representation of the hot and cold blocks. And then down here, you've got the two air intake and air exhaust. Once this reaches a point where it's stable, you should see a difference of about 2 to 3 degrees or something to that effect between them. If you're not seeing a difference there, you might just need to adjust one of the sensors. Under ideal conditions, this top sensor wouldn't be touching the heatsink, but sometimes with this particular experiment, in order to get a reading that makes sense, it will be just touching. Do be careful though, because they are pretty sensitive. To run the experiment, we flip the knife switch, and we're running at just under 5 volts. and 0.6 of an amp. And straight away we can see a difference in the hot and the cold block. Now this can take about 5 to 10 minutes for this to reach equilibrium or to reach a stable point, but that's fine. That gives you enough time to answer any questions that you've missed or anything like that. You'll want to record your initial temperatures before you flip the knife switch too. You can take these to be your room temperature, or alternatively in the lab, one of the clocks on the wall does cycle between time, date, and temperature of the room. It's up to you as to which one you take. So you can see pretty quickly, we'll just move the legend out of the way, pretty quickly these values are changing. Now, the hot block will obviously be increasing in temperature, and the cold block is going to drop down and off. We do ask you if this makes a good fridge. We're not actually asking you if it makes a good fridge. I don't want to know about your wine and cheese. I don't want to know if it makes a good wine fridge either. We're asking you, does this noticeably cool down? And the answer should be pretty straightforward once you see the numbers. So we're at a point where we're almost stable. We can see the cold block has dropped down to about 10.6 degrees almost at this point, and the hot block's sitting up at around 30 degrees. Our air intake and air exhaust have a difference of around 1.2, maybe 2 degrees Celsius, something like that. You do expect to see a difference between them. They shouldn't be the same. For the purposes of this demonstration, we won't worry about that too much. This scale will auto-adjust, so you don't have to worry about shifting it or anything like that. But once you've got this to a point where it's stable, you don't really need to do much else but wait. So this initial part of the experiment gives you some indication as to airflow and heat transfer and the inherent efficiencies or inefficiencies of the system. The thing we're asking you is, we're not asking you to give us a textbook, we're asking you to interpret your data. So look at what your data tells you and give us an answer based on that. So we're now pretty stable, rather than sitting here for 10 minutes, and well, 10 minutes for me and maybe 30 seconds for you. With the magic of editing, we'll continue on. So, through the magic of editing, we can see that this device is now fairly stable in terms of its temperatures. It's going to fluctuate a little bit. It might still continue to drop a tiny bit, but for the purposes of our demonstration, that's okay. The next thing you're asked to measure is, remove the insulator and then look at how that impacts your temperatures. Now, with the way the instruction's written, we do occasionally have people simply remove the insulator and then put it straight back and go, nothing happened. That's not what we're asking you to do. Take it off and give it a few minutes. You should see some change between T1 and T2. You would expect that because it's now no longer insulated, that the cold block should start to heat up a little bit. It might take a couple of minutes for this to happen, but that's fine. There's a lot of waiting in this experiment. You'll get used to it. As an aside, while we're waiting for this data to accumulate, on Pasco you have a bunch of useful tools in order to look at your data. Up here you have one that looks like a crosshair, and as the pop-up says, it's add a coordinate tool. You can do multi-coordinate or just coordinate delta. Multi-coordinate's fine. And as you move it along, it's going to give you the time in seconds, and we'll just move this guy out of the way again. Time in seconds, and then temperature. So on the bottom there, we could see our cold block is, we probably got down to about 8.6 something, and without the insulator, it's gone up to about 9.3. Our hot block has stayed fairly consistent. It's changed a little bit, but nowhere near as much as our cold block has. Once you've given this a few minutes, you put the insulator back on. For the next part, what it asks you to do is to turn off the fan. Now this part we do stress. Please don't let the hot block or the cold block get to a very high temperature. In reference to this device, that's anywhere up into your 90 degrees. You should see an effect pretty quickly. So, carefully, Turning off the fan. Fan's off. So we no longer have airflow. All we have is just the air that's stagnant and present around our heatsink and our device. And we should start to see a rather marked difference in the temperatures. Immediately you can see the hot block is actually starting to increase in temperature. We've gone from about 34 now up to 36. That's probably not 2 degrees. It's not a lot in day-to-day terms. Well, if you're used to a Brisbane summer, it's not. But day-to-day, you can see straight away that is a pretty big difference. That's also hotter than, room temperature. The cold block, on the other hand, it's also heating up. You don't need to run this path for very long. Give it a minute, maybe 2 if you're really curious, but we don't really want this to run hot. What we want to see is just have the device heat up for a little bit and then record those measurements. So we'll turn the fan back on. One important thing to remember is throughout all of this, you don't need to turn the recording off. You can record your data the whole way through. With the fan running again, we can immediately see the hot block is starting to decrease in temperature. The air exhaust has changed as well. And our cold block, which has been slowly creeping up in temperature, will eventually revert back and start to cool again. Now, once you've got all your measurements, once you've recorded everything you need, you can basically hit stop, and that will stop recording the experiment. The other thing to remember too is once you're done getting all of your data, you will flip this knife switch back up just to the central or neutral position, and that will be your experiment done. That would be all of your data there, and then you're free to analyze it as you need to using the built-in tools of Pasco, and then enter that into your performer. So we'll just click, well, to show you what happens, we'll take the knife switch, flip it up. The voltages just go a bit funny again, that's fine, that's normal. We haven't turned everything off though, so it's still recording, and you can watch as the temperatures pretty quickly nosedive back towards room temperature. That's not really important for your experiment, but it is interesting to see nonetheless. Since we don't really need the rest of this, we click stop. We would record any data that we need from this using the built-in tools as mentioned. Let the fan run for a little bit, and then when you're ready to run part B, let your demonstrator know, they'll come over, they'll set you up.